All right, hell yeah. So we have what is engineering? You know what I mean? Someone commented, I'm going to college in engineering, and kind of like, why? Why did I choose that? Nah, that wasn't the question. But anyway, they want to know what to expect. And it is like, why do you choose engineering? It's because you're good at math. 100%. If you're good at science, well, then you got to figure out what science you're good at. You know what I mean? I mean, if you're good at chemistry, that's kind of well, that's more lean. If you're good at physics, hell yeah, that's engineering. I don't think anyone thinks they're good at physics. Now, I might be just joking around on that one, but physics is, I think, one of the hardest. And like a physics textbook is just, they're awful. You know what I mean? And it can be. So that's going to be your first year it's going to feel like high school on steroids, because you're going to have to take physics for your freshman and sophomore year. But damn, is that class just complex. And the reason we take physics is because physics explains how the world works. But then, you know, if you can make it through those first 2 years of physics, yeah, you'll be using physics forever. But when you actually get into the second and third and fourth year, hell yeah, then you get specific. And it almost feels easier, you know what I mean? And so your second year is kind of that transition where you're just like, yeah, the problems are hard. We're doing physics problems for sure, but they don't seem like physics problems out of a book. For some reason, like the switch is flipped, and you're like, hell yeah, we're learning how the world works, you know what I mean? So I think that's the take-home point, is like, physics is how all these subjects, physics, chemistry, and then biology, you know what I mean? And this is the reason why you're not an engineer. I mean, this is the reason you are an engineer, because you're not excelling at biology, or you know what I mean? Like you're more over here in the math, and but you don't want to be a math major. You know what I mean? You don't want to be a math major, and hell no, you don't want to be a physics major, because physics is hard. But if you already think you have a grasp of physics, and you want to know everything about how the world works. You know what I mean? You were born on an earth, and you're just like, oh, hell yeah, like, tell me it straight. Then you want to know physics, and you want to become a physics major. But if you just want to know how things practically work, you know what I mean? You become an engineer. You're like, hell yeah, let's build and there's a lot of fun things you could do, especially with mechanical engineering. That's what that person is going into. I chose to go into environmental engineering, and just, I don't know, just kind of sounded interesting. That's 100%. That's the only reason why I went into it. And then halfway through, I was like, oh, I should have done mechanical. Because hell yeah, I mean, if you want to sell a product to someone, or you know, design an amusement park ride, or you know, anything fun, is probably mechanical engineering. I don't know. In civil engineering, well, I mean, if you think it's an accomplishment to build you know, a city and a building or a bridge, hell yeah, those are huge accomplishments, and you do it. And so there is an element of engineering that like if you want to be a coach for a sport you have never played, you know, become an engineer. If you want to be a conductor but aren't too excited or have never played an instrument, become an engineer. You know what I mean? So that is kind of the interesting thing about engineering. You learn how to conduct an orchestra even though you've never played an instrument. And it's so true, because I mean, think about it. Like, if you're the engineer, that is, from a civil engineering perspective, it's crazy, because you're going to be the one that's going to be able to build a building, you know, even a 4-story one up to 40 stories. You know what I mean? Or a huge skyscraper. You know, sky's the limit on that, and it's going to be your calculations that you know, or you know, part of a team or an organization that is making those. You know what I mean? You're the orchestra in making sure that design is working. So that's fascinating, but that puts a huge responsibility and a huge disconnect, because from like, let's say the civil engineering perspective is just like, well, you should, the first year you should be welding. You know what I mean? You should be playing around with metal and for sure steel. because there's only a couple materials out there. Steel is one of them. Concrete is the other. And then, so that's what differentiates civil engineering from mechanical engineering. Is mechanical engineering is like, nah, I don't want to build big things. You know what I mean? I want to build parts that are part of a structure, part of a whole. You know what I mean? Even like a well, you know, even a huge amusement park or a car or you know, like a ski lift, or, you know, anything cool from that perspective. It could be considered way cooler than just building infrastructure from a civil engineering perspective. All right, and mechanical engineering, you're right at that boundary of like, well, you do know how to make something small and big at the same time. So it's a pretty cool discipline to go into. I just know our department had a huge civil engineering department, and then environmental engineering was kind of part of that. So anyway, but this will be kind of for the mechanical engineering perspective. And why wouldn't you go into physics? Well, from the engineering perspective, you're basically working with mass, and because hell yeah, you can build stuff out of mass. You know what I mean? And so you're already taking a clump of mass and being like, hey, I really don't need to know its chemistry. You know what I mean? And at that level, someone else is gonna, you know what I mean? Just give me the steel molecules, and I'll put them, you know, to good use. I'll make a climbing carabiner. I'll you know, make whatever out of it. Just give me the actual material. So I was surprised. In mechanical engineering, you take like 1 year of chemistry, where I was taking like definitely a year and a half for sure. But then when engineering, like basically you're taking math and physics. Those are your two biggest subjects your first 2 years. And you should be focusing on them equally, and you know, for sure, because the math is what allows you to understand the more complex concepts, even though things get easier, because like hell, textbooks will have, you know, crazy amounts of math to like prove something, you know what I mean? And then they'll pop out an equation, and guess what? You just go use that equation for the rest of your life, and you'll be like, well, I kind of understood the math, but you don't have to use that math every day. So the math after graduating that you'll probably have to use, you know, every once in a while will be like simple integrations. You know what I mean? And that's it. Even though you take hella math to learn pretty complex, you know, calculus. And then from the physics perspective, well, you know, the full physics textbook, you know, can really get boiled down. And as the years go on, you actually, same thing. You take concepts and then you chisel out equations. So mainly, as an engineer, especially ones that are going to forget everything, is just like, hell yeah, give me the equation, give me the problem, and I'll use the equation for the problem. You know what I mean? I'll get, if I have two unknowns, I'll find two equations, and we'll put them together, and then we'll be happy. Alright, so then there's this other perspective. Alright, so there's the other perspective, like what is engineering from the physics perspective? It's F equals ma. And we're basically saying that, hey, we're going to be using stuff that has mass. Everything that we build is gonna have mass. From the civil engineering world perspective, these bridges are just going to sit here, and so they're not going to be moving. But maybe from the mechanical engineering perspective, you know what I mean? Hell yeah, things are going to be spinning, and you have components that are going to be doing that. But at the end of the day, we use this F equals ma equation, and it gives us it's exactly what's happening in our universe. You know, if we can observe a mass, and we can observe motion, or you know, like a change in velocity, then we know something about this side. And from most, or the kind of the simplest perspective, if we do not observe that something's moving, like a bridge, well, this side, the acceleration is 0. But guess what? We have a big Earth underneath us, so there is, you know, this stuff has weight. You know what I mean? And why does it have weight? Because you have the Earth, the center of the Earth is, you know, and the mass of the Earth is pulling this mass towards it. You know what I mean? You have a force is equal to gravitational constant, mass 1, mass 2, radius squared. You know what I mean? And it's crazy that this never even gets taught for like a split second. We just go straight to the fact that this m1 m2 over r squared is, well, this is the F side of the equation. That's going to equal m1a. And then the m1's cancel, and then all this stuff we just call gravitational constant. We just call it little g. So it's just so fascinating that any time that we see a weight of a component, we just say that weight is mg. But like literally, that's where it comes from. So from the well-rounded engineering perspective, you should always be figuring out what the underlying, you know what I mean, like what's the foundation. And I think I can make definitely a lot of videos on this F equals ma that help that foundation. Where I can pick up a physics book, and I ain't going to solve it the way they do, but I'm going to use, you know, my foundation of the fact that, hey, a physics problem is going to have some sort of mass they're talking about, and is it moving? You know what I mean? Maybe. Or maybe they're just pulling on springs, and then once they do, guess what? It's not moving, but we've just generated forces. You know what I mean? So then, you know, a lot of my videos are doing the free body diagrams, and that's not for this one. But, yeah, we don't have that MA side, but we do have the force side. And once we have identified one force, well, if we've identified one force on this side, we need to have forces that balance. You know what I mean? And because this thing is just not... Because if you have any mass and one force on it, and it's in the center of the universe, well, it's going to be going that direction with a velocity and change in velocity. You know what I mean? It's just me going faster and faster if that's the case. But we do not observe that, so then we can go back to Newton's laws and see how that applies. Well, it means that these two tensions have to equal that, and you know what I mean? Then we'll have a force of this one in that direction just a little bit, so this one has to be in that direction. But yeah, and then it was just fascinating, because even today I was just like, well, that is a fundamental principle of... like if I just have a mass, unless it's in deep space, it won't have any forces on it. But since this mass is close to the Earth, hell yeah, it's gonna have at least one force on it. And if it has one force on it from this equation of Kepler, it has to have, and I observe that it's stationary, it has to have another force. And this is super important, because now this mass is actually getting, like, what does it mean to, so if we have F equals ma, and we don't have acceleration, get some more light, and we don't have acceleration, and let's say we don't have any forces. I mean, the only way that's possible is you'd have to get all the way away from all the stars, and you just have to be in the deepest, farthest location in space to have a chunk of mass with no forces on it. So this is cool because, I mean, if you're anywhere in the observable universe, we already know that you can at least have a gravitational force. There's going to be at least one force on it. And if there's one, there has to be a balancing force if you witness no acceleration, like on Earth. And I don't know, it's just kind of fascinating. That means that this mass is going to be squished. You know what I mean? You know, no mass is not squished. So you know, basically, if this side is 0, what does that mean? Well, you're either going to have a mass that's squished, or you're going to have a mass that's stretched. Because it is possible to, you know, even have a weight of mg, but you might be tensioning this, you know what I mean? Let's say it's this way. So you have a mass and it does have an mg, but you put it in a machine and then start tensioning it. Well, now you're stretching it. And it's still visibly not accelerating across the universe. But so just this side of the equation still is significant. It means that if you do observe 0 on this side and you're within the normal part of the universe, hell yeah, that mass is either going to be squished or in tension, you know what I mean, or deformed in some sort of way. And Yeah, because that was the other thing. It's either squished in tension, or it could be, sheared. And because I definitely want to make more videos on shear, because it's a bizarre concept for a mass just to be, kind of torqued out like this. And like right here, if we had a force this way and a force that way, we'll call it P. These are unbalanced. This thing would just be spinning in outer space. But if we still took it from something where we observe that it's not moving, well, then the torque's that way, so it has to have a balancing torque the other way. You know what I mean? So it's got to be this way and that way. So now, just those three fundamentals can really explain. I mean, that's what you're going to be doing for 4 years. You're going to be right in this part. For the most part, or you could be doing some cool stuff where, hell yeah, we're going to make a part that's spinning, and that part's no longer zero. But foundationally, it's just fascinating that things stem from this. And I think that is a very useful concept to be like, well, what is the basis, fundamental understanding of what we're doing? And just basic engineering, it's F equals ma. Where we are going to take chunks of mass and we're going to do cool stuff with them, and we want to be magicians and know exactly what's going to happen. We're going to be like, hey, this bridge is going to stand for 100 years, and then we're going to demolish it, and then no one dies. You know what I mean? That kind of stuff, that's a magic trick. Just the fact that you can do that. Now, that's where you're going to be. And the math is still rigorous. But you're at the end of the day, sometimes it gets easier. Like I said, sometimes it's just like, well, give me the equation. I'm just multiplying and then dividing, numbers, and then getting some answers. You know what I mean? So that's the cool part about it. How it kind of feels like it gets easier as you get past those sophomore year classes. I mean, you just get more specific. But this is like, if you are, it's such a young time, especially like right out of high school, to be like, well, what am I doing? Because if you really are interested in like understanding why things are why they are, like why life is why it is, you would want to get a PhD in physics. You know what I mean? I don't know. You know what I mean? I think you would. You would want to get a PhD in physics if you're really interested in knowing kind of the aspects, because we're just taking chunks of mass, but we also know that mass is made out of atoms. Atoms have protons, neutrons, and electrons. Like, if you want to take it a step deeper, you get into chemistry. You know what I mean? But if you want to take it at the farthest reaches, you would want to you'd want to stick with physics and just hardcore physics, and then you'd have to back it up with some hella math. So those two subjects, where engineering is kind of splitting the difference. Give me a little bit of math. Hell yeah, give me a little bit of physics. I'm gonna run with those, you know what I mean? And we're gonna have a good time. We're gonna make cool stuff. At the end of the day, it's gonna give you the knowledge to do a lot without getting hella bogged down into like Alright, but I would say engineering is heady as hell, where it's just like, at the end of the day, it's just like, well, I'm going to go to class, I'm going to learn the concepts, I'm going to get the equations, and then I'm going to apply them. You know what I mean? But in that process, the fundamental understanding can get lost. You know what I mean? Of just like why and who cares. And so there's two different aspects that, should be on every engineer's mind, and that's why I'm going to do my little channel here. Because at first, I was going to start this channel of like, just guess. You know what I mean? And so, hopefully, within the next week, one of my videos will be, hey, you should be able to, I can give you this equation. The first equation you learn in material mechanics is strength is force over area. And if you have an aha moment, you know what I mean? I had mine years later, it'd be like, whoa, I should be able to, from this equation, design the Empire State Building, or tell you the most fascinating fact about the Empire State Building, the magic trick part. Like, hey, if it's built of steel columns, what's the size of the steel columns? You know what I mean? What's the area, like if they're wide flange beams, Like, what's the cross-sectional area? What's all this area if they're made out of steel? Like, what is that number? And could I just rattle that off in a 5 minute, but more like, for my style, more like a half-hour, 2-hour video? And then I could do it 2 different ways. So even just from that, it's like, well, the Empire State Building has a huge amount of mass. Steel has a strength of 58,000 pounds per square inch, and so you would divide the weight of the Empire State Building, which you can, which would be the force, because that's a mg, that is a force, and if you're trying to find area goes up, so you do the force divided by 58,000, or the weight of the Empire State Building's hella, divide that, and you would get the area of metal needed, you know what I mean? And let's say there is, something that's, some of the literature says that, there's 200 columns, but if you actually do just the vertical part, it comes down to, like, let's say 80 columns. You know what I mean? So you take that area, divide by 80, and you just have the square inches that you would need of steel. So just right off the bat. And then the other thing, because it's so fascinating, you can make videos within like minutes. If you treat, and if you just say, hey, I just want to know these columns on one side of the building, and we're going to put a hinge on the other. And what's going to take a building down? Well, it's wind. You know what I mean? Huge amount of wind. So we're going to do 100 pounds per every square foot of surface area. That's going to give us a number pretty easily. And then, hell, let's just put that at the worst possible location right there. So we're going to have a P force right there. And we're going to say, hey, nothing else is holding except the columns on one side. And now you're just down to like 20 columns, and what we have is just leverage. That's the crazy thing about mechanical engineering is well, I gotta take a pause. Oh yeah, we got this. It's the strength of a material, but then it's really easy to see, like, hey, if I have this, bolt, and then I pull on it, well, sure, it's got a surface area, and then I know, like, how much force I can pull on it. But the second you get into, like, a bridge, you're like, well, now what? We all know that bridges are real weak, and so, but then it's just leverage, you know what I mean? So the simplest thing is, like, hell, a cantilever is just, you know what I mean? This is a hinge, and now you just have like a roped connection right there. And it's the strength of this rope that's actually holding up this structure. So if this is the P down, it has a torque of P times this length, you know what I mean? And then it can only be resisted by the tension in this cable and then this smaller distance. So even with the Empire State Building, take that wind load by the height of the Empire State Building, and then pH is going to be equal to, well, the tension in all of those columns, and now you just have 20 times area times, and if area is in inches, so you have pounds per square inch is the strength, back up to here. So if you wanted to find the force, you would take the area of those columns times the strength. So 20 times the area of one of them times the strength, you would get that number. And then, so the only thing resisting is that number times this distance. And so you would have the force of the wind times the height of the building, and then the distance, the max tension that these columns could take, times that distance. And what you could find is if it's in check, you know what I mean? If this number, or no, you would find the tension. There you go. You would find the tension, and then you would match it with the force max that those columns could take. But anyway, holy hell, so that was definitely more complex than it needed to be. But that's a napkin calculation. So you could be like, hey, we want to design the Empire State Building. Well, what's going to topple it? Friggin' wind. You know what I mean? Wind just blowing it and then just blowing it over. You know what I mean? Or stressing these. You know, and that is if you have a cantilever, a building is just a cantilever that's just, so if this is the Empire State Building sideways, guess what? That's the wind. and now you just have a huge cantilever that's trying to pull it, bend it. And usually a cantilever is kind of the one of the weakest designs when it comes to, well, obviously it's hella weak when it comes to, compared to the supported bridge. All right, so, but yeah, so that's the things that I would tell engineering students to be like, yeah, just get the basics and see how far you can run with just the knowledge with like simple concepts. And just know that when you are working on stuff that's hella complex, like just never lose that or keep reinforcing like what's the fundamentals, like who cares, like just and these are all physics. Like the first chapter of physics says you should always do this. If you want to know how many blades of grass are in your backyard, you know what I mean, you could take 1 centimeter. You could take, well, just like 1 inch. I don't know. I would take 1 inch. I would take a quarter of an inch. Take a quarter of an inch. See how many blades of grass are in a quarter of an inch. So times that by 4, you got 1 inch. Times it by 144, you got a foot. And then I don't know. Figure out how many square feet are in your backyard, and you know exactly, pretty accurately, how many blades of grass you got. So that type of stuff will get you really far as an engineer. Just like, dude, just guess. And don't worry about it. But yeah, else. But I know that when you're trying to get problem solved, I think that there's not a lot of effort put in to be like, hey, show me the process, and giving credit for that. Because you might be able to come up with different ways to do it that are just way better than like the classical. Like that's why I hate all physics problems, because they're just like, require very specific answers, or they're trying to trap you into using, I don't know, kind of just one way to do it, when you can use the fundamentals and potentially get there from many different ways. So anyway, so that's going to be my idea of what is engineering and why you would go into engineering, because you like math, but you don't like math enough to just be like, oh, we're all about math, because that would be heady as hell for me. You know what I mean? Just the fact that you have something to work on. In mechanical engineering, hell yeah, because you probably will have hands-on approach. Civil engineering, no. You literally are you are the conductor of the orchestra and have never played a musical instrument in your life. Like plenty of engineering students they're on their game when it comes to math and education, but have probably never picked up a welder. And it's just it's I don't know. It's a weird combination, that fact. But that's just the fact of life. That's why engineers are who they are, and it's helpful to pick up a welder. That's for sure. Reason you don't go into biology is just you didn't want to do all that type of science. You know what I mean? Chemistry and biology. If you thought math, and it's usually centered around math. If you thought math was your strongest subject, you'll go to engineering. But if you're just like, math was okay, but you liked sciences, well, hell yeah, you're going to go that route. All right, hell yeah. And then all 4-year degrees, could just be the starting point for your education. Because even with mine, I don't know, I got out pretty cheap, but I didn't want to spend any more money, you know what I mean? And, but you can always get an undergrad and then maybe totally switch gears, because, after 4 years, you might be like, oh, hell yeah, I definitely want to know how the world works, to a high degree, and be on that cutting edge of understanding. But I don't know, I think you get that aspect, you know what I mean? Every branch of education has some sort of engineering, because all engineering is like, hey, we're really hyper-focused on a certain aspect that we're really good at learning, and then we're going to use that to do cool stuff with, you know what I mean, or explain cool stuff. And every aspect of math, physics, chemistry, biology, even and then biology floats into like, this is kind of the joke. It's like, why are you in engineering? Like, why aren't you in figuring out how the human mind works? You know what I mean? How humans operate. You know what I mean? Because you don't want to be anywhere close to humans. You're probably antisocial, so you're probably not going to do this. You're not going to go into psychology, because you're just like, yeah, humans are messed up, and so why would I want to take 4 years to realize, yep, humans are bizarre creatures. You know what I mean? So that's why math and physics are just like, hell yeah, we can learn tangible stuff about reality. But no, I'm kind of like, I just think it's the human aspect is just super fascinating. How like you can have all this education on one side and then just the human element on the other. There's something very fascinating about that. That yeah, you like, I mean, math and physics, yeah, we'll make more leaps and bounds, but just in basic human psychology, and maybe there's nothing there. You know, maybe it's a ghost where you're just like, it's just patterns, and you're trying to find some answers in bizarre, chaotic patterns of the humans, man. But anyway, so that's why you're definitely, so there's definitely an echelon between math, physics, engineering, and then engineering is kind of encompasses all, because you could be a computer science, you know what I mean? So physics kind of is branched into electrical physics and then Newtonian-based physics. And yeah, if computers aren't your strong suit, you'll probably, because if you go into physics as a whole, you're kind of a more well-rounded individual. You're going to be, hell yeah, math, computer science, and electrical engineering. Where from the electrical engineering perspective, I don't know where you fit. I think you do like physics, but don't want to get a PhD in physics, and then you go electrical engineering just because it's kind of at the, yeah. I mean, that gets you closer to how the world works. You know, just from jumping off on the works of Einstein and stuff. I mean, so that's where engineering is kind of like a Newtonian dead end of just like, okay, we're just working with F equals ma. But at the end of the day, we need more of that. We need more people that understand F equals ma. It's enough because it's what happens with our world at the Newtonian level, and you can do hella everything with it. So anyway, so that's I don't know. I'm satisfied with this video, but whatever. It's just kind of my thoughts on it. And so thanks for joining me. And guess what? That's a video.